Everyone, and thank you for joining this session. I'm presenting work done together with my colleague Javier Hanumanfo, and we are both from Institute for Web Science and Technology at the University of Koblenz in Germany. The title of our paper is Early Warning Prediction of Student Housing Dissatisfaction to Support Targeted University Interventions. And in simple terms, we build a small practical system that helps universities spot students who are unhappy with their housing early enough to actually do something about it. I will walk you through why this matters, how we did it, what we found, and how it could be used responsibly. Let's start why it is important. Housing is not a side topic, it shapes the student's everyday capacity to study. A room that is too expensive, too noisy, or in bad conditions affects sleep, concentration, and mood. It also affects engagement. Students struggling with housing participate less in campus life. But here is the operational problem. Universities usually find out too late. Complaints arrive after things have already escalated. So the question we ask is simply, can we spot serious housing dissatisfaction earlier in a way that lets student services actually help? Organize the work around three research questions. The first one is about prediction. Can we identify students at serious risk of housing dissatisfaction using only survey questions that don't already give away the answer that students are satisfied? RQ2 is about deployment. Once we have a risk score, how do different thresholds change the balance between missing cases and overwhelming staff? And the third research question is about transparency. Which signals are interpretable enough to actually guide the support action instead of just being a black box number? These three questions correspond to the three things we think a useful early warning system has to combine: accuracy, operational realism, and explainability. Data and what exactly we're predicting. We used a housing survey from the University of Koblenz with 158 students. The survey covers demographics, housing characteristics, costs, services, and fit, the kind of information a university can realistically collect. We label a student as at risk if their overall housing experience score is 3 or lower on an 1 to 5 scale. That gives us about 32% of students in the at-risk group, 51 out of 158. One important detail here is that we removed any survey questions that basically already ask about satisfaction or overall experience. We call this leakage aware. Otherwise, the model would just be learning the answer from a question that already contains the answer. Here is the pipeline in 4 steps. The step 1 is pre-processing. We encode the survey responses sensibly. Number-like entitlements become order scores. Categories are one-hot encoded, and we impute missing values inside its false so no information leak. In step 2, training, we compare 4 models: logistic regression, random forest, histogram gradient boosting, and a small multi-layer perceptron. In the next step, it is the validation step, 5-fold stratified cross-validation with a fixed random seed of 42, so the results are reproducible. In step 4, it's the threshold tuning. This is the step most papers skip, and we don't just take 0.5 as the cutoff. We pick a threshold that makes sense operationally. All 4 models are simple enough that the university could actually deploy them without heavy infrastructure. Look at how the models actually perform. The random forest gives us the strongest result, a UC of about 0.8 and a tuned F1 score of 0.73. The logistic regression is very close. This is important because a simple, transparent model is easier to communicate and audit. The MLP, the neural network, underperforms here. That's what we expected with only 158 rows and tabular data. Simpler model almost always win. And we should notice here the orange bars. The tune F1 are always higher than the default 0.5 threshold, which gives so threshold tuning isn't, let's say, a step that it is redundant, it materially changes performance. Here is some results about the threshold, and basically this is one of the main methods of the paper. So normally most papers stop after reporting accuracy, but for a real support workflow, that's not enough. The threshold, which is basically the cutoff above which a student is flagged, is a policy choice, not a technical one. So if you set a lower threshold, you catch more at-risk students, but you flag more people and your staff has more outreach to do. If you set a higher threshold, you save staff time, obviously, but you miss some students who generally need help, or those, let's say, that they are on the borderline of this threshold. So the right choice depends on your priorities, your capacity, and the moment in semester. This is something a university has to decide consciously, and it shouldn't be hidden inside the code. What these numbers look like in real life. At our chosen operating thresholds, both random forest and logistic regression identified 38 of the 51 at-risk students. To do that, the system flags between 64 and 66 students total. So about 2/3 of flagged students are genuinely at risk and 1/3 are precautionary contacts. The recall is 0.75, almost, meaning we catch about 3 out of 4 at-risk students. Concretely, this means that if we imagine a student service team gets a list of about 65 students to invite for a short check-in, which is basically physical workload. And about 13 at-risk students will still be missed, which is exactly why we keep saying that this is a triage, not a final answer. Human judgment or human oversight still matters. Score is on its own isn't very useful. What helps is knowing why a student is flagged. So using permutation importance, we looked at which features matter most for random forest. The top signal is expectation alignment, basically the gap between what students expected before they arrived and what they actually got. That points to clearer listings and more honest photos. Next is affordability pressure, which points to financial counseling or emergency support. Then housing instability, students who have moved several times. That is where contract briefings and mediation can help. Privacy and space and services responsiveness lower, but still important signals pointing the room standards and faster maintenance. The key idea here is that every signal maps to a concrete action a university can take. So we don't just want a model, we want a workflow that a university can actually run. So the step one is an early light survey using click-aware questions. In the first step, we can have the model that produces a rich score, ideally with some indication of uncertainty. The step three is about the support team that picks a threshold based on staff capacity that week. And then on fourth step, we have the triage review where humans look at the flag list, sometimes adjust it and devise how to reach out. And in the last step, we have the monitoring step, which after some weeks review what happened. Did outreach help? Was the threshold sensible? And then recalibrate. The whole point is that in every step leaves space for human judgment. The model is the prompt and not obviously the decision. Ethics not as a final paragraph, but as a part of the system itself. On the left side, what the system is for. Prioritizing supportive contact, offering help, never labeling, telling students also clearly what the data is used for, and calibrating a new survey waves come in. On the right side, what it is not for. It should not decide who gets housing. It should not evaluate behavior, not punish students or landlords, and it must never replace normal access to support services. A flagged student should receive an invitation, not a verdict. Four principles run through everything: informed consent, minimizing the data we collect, keeping support separate from enforcement, and regularly auditing when the model makes mistake. Here are also the limitation and what we plan to do next. The sample, first of all, is very small, 158 students from one university, one survey wave, and it's cross-sectional. We can yet say what happens over time. The target itself is self-reported, so we are predicting a subjective signal, not an objective outcome. We also didn't yet check calibration, meaning whether a 70% risk score really corresponds to a 70% chance. For the next steps, we want to validate on later survey waves, we want to replicate across institutions, we want to do calibration and subgroup error checks before any real deployment. And most importantly, we want to pilot it with the student services team and actually measure whether the outreach helps. Because the model is only valuable if it changes outcome. We have here three takeaways. First, early warning predictions is feasible even on small institutional housing dataset with simple models that any university could deploy. The second is that threshold, not just accuracy, decide whether a system is actually usable. Picking a threshold is a policy decision and should be made consciously. The third is that risk scores are most useful when they point to concrete support actions, not when they become labels attached to students. That's the heart of our paper, connecting predictions to support transparently and ethically. Thank you very much for listening. I would be happy to take any questions. Our email are on the slide.